who just finished her master's studies with me. She's now a research associate at the research center. So Laura, the floor is yours for your presentation on steel making.
Okay, thank you, JP. Can you listen to me?
Yes, we can hear you.
Okay, so I've been facing some connection problems here, but I'll try to share my screen and then, okay, share screen 2. Okay. Can you see it?
Yes.
Okay. I just need to connect the audio. So I'm gonna mute myself. I can find a word like to share the audio.
It needs to be done before you share your screen.
Okay. 1 second. So I'll be
So
sharing.
when you share, I don't know on Mac, but on the top right, there's
Okay.
something saying automatically optimize, and right beside that, there's like a speaker saying share your computer audio.
Sweet audio. No. Okay. Anyway, so I will do live. I'm just worried about my internet connection, and it's a little bit noisy here, but let's do it live. I won't be opening my video, so hope you don't mind. Okay, screen 2, share. Then okay, can you see it?
Yes, we can see it.
Okay. So okay, so now it's full screen. You can see everything.
Yes, all good.
Okay, good. So let's start. So hello, everyone. I'm Laura Pressi. As JP has just mentioned, I joined CRT in 2019, and I came to Canada to take my master's here in this research group. So last year I concluded, and now I continue in the group as a research associate. So I'm going to be presenting my project, which studies the impact of controlled impurities content and microstructure on the mechanical behavior of 13 chromium 4% nickel. So to give a little bit of context here, I would like to talk briefly about hydropower, which is known as the most relevant contributor of all renewable energy sources. So in hydroelectric power stations, the hydraulic turbines, they are critical components as they are used to convert the kinetic energy of water into mechanical work, which is then converted into usable electric energy by a generator. So due to its operation mode, the water turbines they can present several issues as they are subjected to several stresses in service as larger cyclic loads, which can cause their premature failure by fatigue. So it goes through a fatigue process of crack initiation, crack propagation, and then a catastrophic failure. And it can also present surfacic cavitation and pitting corrosion that is caused by the flow of fresh water on their surface. And these, they are ideal nucleation sites for cracks. So here highlighted in blue, we can see an example of a turbine blade with surface cavitation and pitting corrosion. So in order to minimize these problems, several studies they have been carried out with the objective of developing new materials for the construction of rotors, and also the recovering of these cavitated regions. So, as a continuation of Hydro-Quebec's research study, a bigger project entitled FATCO was designed. This main project concerns for the damage to hydraulic turbines and ceramic shaping industrial equipments from fatigue corrosion, and material heterogeneity. So my project is just one part of each, which aims at understanding and quantifying the impact of the presence of critical impurities such as oxygen, sulfur, phosphorus, nitrogen, hydrogen, and carbon on the formation and also precipitation of inclusions in this stainless steel. So more specifically, here we want to define how these inclusions they impact the mechanical behavior, the corrosion, and also the microstructure properties of this stainless steel. So we know that with the improvement, sorry. So since we know that with the improvement of some more suitable materials, this hydraulic turbines they started to be manufactured with the C6NM. So highlighted in blue, we can verify the chemical composition of this cast steel, which contains between 12 to 13% of chromium, 2 to 5% of nickel, and as a requirement of Hydro-Quebec, less than 0.03% of carbon. So this material, it's classified by ASTM as soft martensic stainless steel, and it presents appropriate mechanical properties considering the request that is imposed on these equipments. So since we are aiming to study the presence of impurities in these materials, we had to synthesize these polluted samples to be analyzed. For that, we first had to understand the process of steel production and after adapt to our reality. So here we have the basic steps of the process to obtain this material. Briefly explaining here, first we have the alloying process when the material is melted and alloyed, and then it goes to the cast process where it cools and solidifies. And this S-cast structure so needs to go through a process of heat treatment in order to lower the hardness of the material and obtain the desired characteristics. So highlight here in red on the right, we can see the microstructure of this steel. So knowing that I have just mentioned, so we started to design our experimental methodology, keeping in mind the research question that we would like to evaluate the impact of the presence of the undesirable elements. So we first developed a DOE where we would like to synthesize billets containing different levels of oxygen. So we would be polluting them out with hematite. We also want to produce samples with various contents of sulfur with the addition of iron sulfide. And we would also be testing different deoxidizers as aluminum and calcium silicon. And we also want to vary the duration of melting process to see the impact. So for that, we considered the elemental composition, and with the raw material that we would have available, we performed a mass balance. So with these results, we use it as an input in FactSage, where we could run several simulations and obtain important information to perform the experimental casting, which was done at the Quebec Metallurgy Center. So in the afternoon, during the FactSage workshop, I will be showing some of these simulations. Here about the experimental methodology that we are using in this project. Here it's important to mention that CMQ, they have induction furnace, but we don't have the availabilities of the technologies that are used in the industry to be able to produce the state of art of the stainless steel. So we are trying to use raw materials that they are really pure to be able to synthesize the samples, trying also to mimic the inclusions that would form in a commercial stainless steel. So here I would like to show the two furnaces that we have used in our preliminary cast operation to validate this approach. So one furnace on the left operates in a controlled atmosphere under vacuum, and it's named Consarc. And the other one is an open system with a protection made with argon liquid being poured on the top of the melt. So I'm going to be focused on explaining the process that we did in the open system furnace. So we weighted the master alloys, and then we placed it in the crucible respecting an order while we started the induction. So during the process, we were checking the temperature to ensure that we have activated the minimum temperature to be liquid. And once we had like everything melted and well mixed, we poured it into a preheated mode. And then after the solidification, we could remove the bar from the mold. So highlighted here in blue, we can see one of the billets of C6M that were cast in this first trial. So far, we have produced and analyzed 11 bars with different levels of oxygen and different process conditions as we used the two furnace, and we also tried something different. In some melts, we checked the impact of not skimming it. So here we have a schematic of the division of the billets that we did in order to obtain all the samples for the analysis. These bars, they were analyzed in two conditions, as cast and also heat treated. So with this analysis, we performed several tests as Sharpie, hardness, we reviewed the microstructure, and we also did inclusion characterization. So now we can check the main findings that we have found. We have checked it. So first one, we were able to verify that this novel strategy to pollute the melt with oxygen using hematite and further mimic commercial alloy by deoxidizing it with aluminum, it was representative. We could check that validating the size, shape, and morphology and also distribution of the inclusions. And we could see that they are directly connected to the melting process, which in our study was linked to the atmosphere of the furnace, like we use the vacuum and the argon dripping. And we could see that these inclusions, they impact the toughness. So we were able like to determine how the oxygen content in the steel impacts its mechanical properties such as toughness and hardness. And we could also learn from this study that only quantifying the oxygen content in the steel is not enough to ensure optimized behavior of the steel, and that there is a formation of some inclusions that are more detrimental than the others. And we could also confirm that the use of thermodynamics to predict the oxygen solubility in the molten steel, which in this case allowed us to identify the primary and secondary inclusions that might form during the solidification. And with doing the SEM and EDS analysis, we could complete the characterization of these inclusions, confirming what we had predicted. So here we are getting at the end of my presentation. So I would like to thank you for your attention, and in case you have questions, they are welcome. Here you also have my LinkedIn, and in case you want to contact me, I'm available. Thank you a lot.
Thank you, Laura. So again, we're right on time, so there may be a little bit of time, but what I'll ask to the attendees, if you have comment or questions, let's wait for the last presentation just after this last presentation that I'm gonna show you. Then we can maybe interact a little bit with the audience. So good news, everyone. We didn't lose anyone. In fact, we gained few attendees until now. So it has been almost 2 hours. So thank you so much for the attention. And it's really, I think it's really interesting presentation. So the last